Hello there. In this video, we're going to discuss the overlying difficulty that surrounds integration. So usually integrals are usually posed as problems to test the sophistication of mathematicians or students, because sometimes they require a little bit of cleverness and some tricks and some knowledge beforehand before you can actually solve that problem. For example, solving basic integrals such as the integral of 1/2 x squared with respect to x is very simple, because we know this by the product. The power rule is just going to be equal to 1/6 x cubed plus some arbitrary constant c. For this video, I'm just going to be focusing on this portion here and not be really focusing on the constant of integration, because typically that's assumed to be there anyway. So of course these problems can become a little bit more complicated. For example, the integral of 1 divided by x. But if you know that the derivative of the natural log of x is this, then you can just state that that is going to be the answer of this indefinite integral. Of course, as you start to make things a little bit more complex, then you get to problems such as the integral of x squared minus 5x minus 2 all over the x squared plus x plus 1. So this you may not be able to recognize quickly to be the derivative of something. So the question then becomes, can you find the answer? So if you know partial fraction decomposition and a couple other tricks on these types of functions, you may be able to find that one representation for the answer is x minus 3 times the natural log of x squared plus x plus 1. So how can you get to this answer is one question. But another question is, how do you know an answer can even be found? So for example, suppose you have the integral of the sine of x squared dx. Can you express this in terms of basic functions like exponential, trig functions, log functions, polynomials, combinations of each of them with addition, subtraction, multiplication, and division? Can you find this answer? And for this particular example, this is an example where you actually cannot find those things. So we say that no elementary primitive exists. That is, it doesn't matter what kind of tricks you have, you cannot express this in terms of functions that are basic, familiar to us. So in this video, we're going to be talking about this problem and sort of what the consequences of it are, and how can we prove actually that this integral cannot be found in terms of functions that we know. So before we get into the detailed discussion of this, let's define a couple terms that we will be using. The first is an elementary function. So an elementary function is what? So it's a function that is representable by a finite number of products or quotients of constants, algebraic, exponential, trigonometric, and logarithmic functions using a finite number of basic operations, namely addition, subtraction, multiplication, and division. So any function that can be represented by these things is what we refer to as an elementary function. Now the main definition of interest is the following. So an elementary primitive of function capital G is a function, little g, that is elementary such that the integral of capital G of x dx is equal to little g of x, or equivalently, g prime of x is equal to g of x. So we say that the elementary primitive of some capital function g is the little function g such that the derivative of little g is capital G. So we say that an elementary primitive exists if we can express its antiderivative in terms of elementary functions. So that is pretty much what an elementary primitive is. So the following theorem, the proof of this theorem is a little bit more sophisticated than I really want to get into. But if you're interested you can visit Louville's original paper of where he proves a more stronger version of this theorem, which is dedicated to Louville. So Louville's theorem says this. So suppose f, g are rational functions. And when I say rational functions, I mean quotient of polynomial functions. So if this is true, then the integral of f of x times e to the g of x dx has an elementary primitive if and only if there exists a rational function h satisfying the differential equation, or simply ODE, that f is equal to h prime plus h times g, or y prime plus gy equals f has solution h. So this is what Louville's theorem says. So if the integral of f times e to the g dx has an elementary primitive if and only if the solution to this differential equation with given f and given g has a solution that is itself a rational function. So that is what this theorem says. So you can use this idea to prove whether a function has an elementary primitive or not. All right, so let us do an example that sort of demonstrates this. So the claim is that the integral of e to the minus x squared dx does not have an elementary primitive. So if somebody were to ask you this question, find the integral of e to the minus x squared, you will not be able to find it in terms of logs, polynomials, trigonometric functions, and so on, using a finite number of operations. So how can I prove this so you don't waste your time trying to figure out if it does or not? All right, so let's do a proof of this statement. So express the integral as the integral of f times e to the g. So we can rewrite this integral here as the integral of 1 times e to the negative x squared dx. So I'm going to equivalize this to be written as the integral of f of x times e to the g of x dx, so that I can use Louville's theorem directly. So here f of x is equal to 1 and g of x is equal to minus x squared. All right, so our goal is to solve the ordinary differential equation given by f is equal to y prime plus g times y. And see if the solution y is a rational function of x. So that's our goal. So using our definitions of f and g, then we have the differential equation 1 is equal to y prime plus negative x squared y. And you can rewrite this a little bit more nicely as y prime minus x squared y is equal to 1. So if you're familiar with ordinary differential equations tricks, you should recognize this differential equation as a first-order linear non-homogeneous differential equation. So if you're familiar with that, then that means you know we can multiply both sides of this equation by some integrating factor and find that result. So my integrating factor is going to be equal to e to the integral of minus x squared dx. So that is going to be equal to, mu of x is equal to e to the minus 1/3 x cubed plus some arbitrary constant c. But if you're familiar with the theory, we do not need to write that. So I'm going to multiply both sides of this equation by mu. So when I do that, I'm going to get e to the minus 1/3 x cubed times y prime minus x squared e to the minus 1/3 x cubed times y is equal to e to the minus 1/3 x cubed times 1. So recognizing the left-hand side is a backwards product rule, we can see that this is the same as the derivative with respect to x of y times e to the minus 1/3 x cubed. And that's going to be equal to e to the minus 1/3 x cubed. So I can take the integral of both sides with respect to x. So that I have the solution to this differential equation is implicitly given by y times e to the 1/3 x cubed is equal to the antiderivative of e to the minus 1/3 x cubed dx. So the question now becomes, well, can I find this integral? In fact, this is another integral that is also not elementary primitive, but let's just define this to be equal to some function called 5x. So this then gives us y is equal to y times e to the negative 1/3 x cubed is equal to 5x. And then I'm going to divide both sides by e to the negative 1/3 x cubed. So I have y is equal to e to the positive, and there's some arbitrary constant c here. So e to the positive 1/3 x cubed times 5x plus some constant c. So let's do this step. I'm going to distribute to sort of perform the analysis. And we have that y is equal to e to the 1/3 x cubed times 5x plus c times e to the 1/3 x cubed. So our next question becomes, is this possibly a rational function? So is this possibly a rational function? When I say rational, I mean p of x over q of x, where p and q are polynomials. So can we rewrite this at this form? So the first observation is that constant is just a constant, and we have this exponential term, and you cannot rewrite this exponential expression as a rational function. It's not even in the same class of functions. So the question then becomes, okay, what about this 5x? Is this possibly equal to something such that the sum of these two things are rational? So the best we can do really is this. We can look at our original differential equation that this is a solution of. For example, y prime is equal to 1 plus x squared y. This is the solution of this equation. So what does that really give us? So we see here that if y prime is equal to this for any xy in the solution, then this is not going to be some constant. So if that is not going to be a constant, I'm going to call it a different constant, say k, then that means when we sum these two functions up, it's impossible to cancel out. Because remember, 0 is a rational function because we can rewrite it as 0 over 1 or 0 over x plus 1 or something like that. So it's impossible for this antiderivative of that other function, phi, to be equal to a constant function. And it doesn't really matter how you think of this. Like, you can consider, okay, well, what if phi is polynomial? Is it possible then? No. If it's logarithmic, is it possible? Definitely not. And if you consider all the other possible elementary functions, then you'll see that this definitely cannot be expressed as a quotient of two polynomials. If that is the case, then what? So that means the solution is not rational. Hence, by Liouville's theorem, no elementary primitive of e to the minus x squared exists. That means you can't find the antiderivative of this in basic functions. And there are several other functions that will have this same exact characteristic. So we've actually given a proof of this function not having an antiderivative. The integral of sine x over x is another one. The integral of sine x squared is another one. The integral of cosine x divided by x is another. The integral of e to the x over x is another. The integral of x divided by the ln of x dx is another. And there's actually an infinitely many number of functions that you cannot find an elementary primitive for. And there's another theorem that actually says that the number of functions that do not have an elementary primitive are actually more larger than the set of functions that actually do have an elementary primitive. So the set of integrals that you actually cannot find is actually larger than the set of integrals that you can find. And this is a very, very important result, because then it actually shows the complexity of integral calculus.